The synthesis of alum. It's called alum because it's made from aluminum, and the reaction takes place in 4 stages, four reaction steps. And so I'm going to break them down in this brief PowerPoint, and then we'll do sample calculation for trial 1, and then you're going to show calculations for trial 2 in your reports to make things easier for you. So we will demonstrate the synthesis of a new product. The new product is called alum. The new product is called alum, and purified by filtration. I'll explain how that's done. And the other reason why, the other objective would have been, if you'd have done the lab, the other objective would have been to find the theoretical and percentage yield of this synthesis of alum. So because it's virtual, we cannot demonstrate the recycling process. So I'll just focus on objective 1 and 2. Okay, so let's see. An alum is a class of chemical compounds that has the formula M standing for the metal. That could be the potassium if you use potassium hydroxide. It could be sodium if you use sodium hydroxide, and other metals that can be used to make alum. So there'll be a metal there, there'll be aluminum, SO42, and then the 12 waters. These are just water of crystallization. We did that, I think, when we were doing formula of a hydrate experiment, when we were still on campus. So water of crystallization. Okay, so it has to have the 12 water of crystallization in the formula. So to make it, we're going to follow these steps. So step number 1, you take your 1 gram sample of aluminum foil, you cut it up, cut it to small pieces to increase the surface area of reaction, and then react it with a volume of potassium hydroxide. And then your solvent is going to be water. Part of the water will be used as a reactant. So if the equation is balanced, 2 portions of aluminum will react with 6 molecules of water and 2 portions of potassium hydroxide to give you 2 equivalents of potassium aluminum tetrahydrate. Hydrogen gas will be released. That's why this reaction, for safety, we have to work it in the fume hood, because hydrogen gas is, when you inhale a concentrated portion of hydrogen gas, it's poisonous, toxic, and of course you'll be coughing and crying. So the reaction would have been done in the fume hood in the lab. So the step number 1, demonstrate an oxidation reaction and a reduction reaction. So this step number 1 is said to be a redox reaction. There's reduction and there's oxidation. So who is reduced, who is oxidized? Let's see. Okay, so aluminum, let's see. Aluminum is a metal, so it has oxidation state of 0. And to your product side, this is where aluminum is. So we need to determine the oxidation number of aluminum. We know that K has a charge of plus, which means everything that's in the bracket will have an overall charge of minus to balance out the plus on K. So this block will have a negative. So now let's focus on that block. We don't know the charge of aluminum, but we do know that each OH has a charge of -1. It's a hydroxide. Hydroxides have the polyatomic anion. Hydroxide has a charge of -1. So we have 4 of them. So I multiply by I multiply by -1 because we have 4 OHs. Overall, the formula has a charge of -1. So I'll say if I sum up the oxidation number of aluminium and I sum up the charges from the 4 OHs, I should get a charge of -1. Let me clean up here to be very clear. Okay, so we have 4 OHs, so it's 4 times -1. Overall, this part here has a charge of -1, so we put -1. So we'll say AL is going to be equal to -1 plus 4. Because this is -4 to the left, going to the right will be +4. AL has a charge of +3. So aluminium is oxidized from aluminium 0 to aluminium +3. Oh, that's definition of oxidation, increase in oxidation number. Oxidation is increase in oxidation number. So AL is oxidized from 0 to +3. So who is reduced? The definition of oxidation is, the other definition of oxidation is addition of oxygen. Water is losing its oxygen to give you hydrogen gas. There's no more oxygen there. So it lost oxygen. So this is reduction because it's losing the oxygen, because we know oxidation is addition of oxygen, increase in oxidation number, or can also be defined as removal of hydrogens. So in water, hydrogens are not removed, it's oxygen that's removed, so it's reduction. So that's why I say that this reaction is a redox reaction. It involves both reduction and oxidation. The product formed, this product here, potassium aluminium tetrahydrate, the product formed is filtered, and then you use the filtrate. So you would have a flask, you would have used a flask and a funnel. The funnel will have a filter paper, so you pour your solution through, the liquid goes through. The liquid that goes through is called a filtrate. You'll be left with black residue. If you watch the video, you'll see those two scientists, they had a black residue after this step. That black residue is unreacted aluminium and some other junk that comes with the reaction. But what you need to go to step 2 is the liquid part that goes through, because this product right here is ionic. You expect it to dissolve in the water, which is the solvent. So we use the filtrate to carry on with this product right here to the next step 2. So this was formed from step 1. It's in the liquid that was contained in the flask after filtration, what we call the filtrate. So you take that liquid and then you add the first portion of sulfuric acid. You take the filtrate and then into the filtrate, you add the first portion of sulfuric acid. Okay, so that's the first portion of sulfuric acid. You're gonna get aluminium hydroxide, so to speak, aluminium hydroxide, potassium sulfate, and water. This potassium sulfate will later on be used in reaction in the last step. So I said first portion. So into the same flask, you're gonna add the second portion of sulfuric acid in step 3. So this will be the second portion. Now, why are you adding these things in portion? Why are you adding them portion-wise? The reaction is very exothermic, so we have to add the sulfuric acid in portions. So there's portion 1 in step 2, and there's portion 2 of sulfuric acid added in step 3, just to control the exothermic reaction. Now, in step 1, sulfuric acid is not much. It's not added. You've not added a lot of sulfuric acid. So what this does is just to give you the aluminium hydroxide, and potassium sulfate. So adding more sulfuric acid, the aluminium hydroxide is going to be converted to aluminium sulfate. because now this becomes an excess. The equations are balanced already. Just know the key intermediates that are formed. So you convert your aluminum hydroxide formed in step 1, use it as a reactant now to react it with the next portion of sulfuric acid. You get aluminum sulfate in step 3, and some water that's released into the solvent, which is the same water. So now we proceed with the aluminum sulfate in step 4, combining it with the potassium sulfate. Okay, your aluminum sulfate made in step 3. So this is from step 3, combined with potassium sulfate made in step 2, and some extra portions of water. You're gonna get your alum. This would have been our end product. So basically, whenever you're doing synthesis, synthesis means to make something. Whenever you're doing synthesis in chemistry, you might do one-step reaction to take you to the product. You might do two-step reaction to get your product. You might do three-step reaction. Sometimes you do even 70. It just depends on the process. It depends on what you're making. So you might keep on doing the reaction to the end. So because there's so many steps, for example, how we've gone up to 4 steps to make the alum, because there's so many steps, there's so many chances of error. And those errors could arise probably from it could be systemic or random errors. So assuming that you don't know, assuming that you don't do any errors, the yield that you'll obtain is called the theoretical yield. In theory, that will be the yield that you should have obtained, everything going perfect and well, is the theoretical yield. Now, being human, we end up making errors, so we get an actual yield. So we'll use the actual yield divided by theoretical yield times 100 to get the percentage yield of alum. But to do that, you need an overall equation of reaction. So going through the processes, the 4 processes, we notice that there are some intermediates that were made and used up in a preceding step, in a subsequent step. So that's how we generate the overall equation of reaction. If you watch the video, the lady explained to you how to get here, but I'm going to briefly take you back. Remember, step 1, we used 2 portions of aluminum and 2 portions of potassium hydroxide. That's step 1. If you've forgotten, let me take you back. So step 1 used aluminum, potassium hydroxide. So we've accounted for those 2. Let's see what next we have. So next it says 4 portions of sulfuric acid. Let's see where that came from. On the reactant side, we have 1 portion of sulfuric acid on step 2 and 3 portions of sulfuric acid in step 3. Add 1 plus 3, you get 4 sulfuric acids. That's how we have the 4 sulfuric acid. And then next it says 22 molecules of water. In step 4, we have 24 portions of water on the reactant side. And then in step 2, we have 2 portions of water on the product side. So if we subtract, you get 22. That's where the 22 came from. And of course, let's look at the product side. I only see 3 molecules of hydrogens and the alum in red. So the 3 molecules of hydrogens came from step 1. But where is everything else? Notice that potassium sulfate is not included because you made it. You made the potassium sulfate somewhere. Let's see, where did you make it? Yeah, you made the potassium sulfate in step 2, right here, but you ended up using it in step 4. So it was made and used up, so it does not show up to the right or to the left. The species that are made and used up are called intermediates. They don't show up in the overall equation of reaction. They are made within the elementary steps and used up within the elementary steps. So they are called intermediates. One of the intermediates is potassium sulfate. It's made and used up. The other one, of course, part of the water because we had to subtract. And then let's see, nothing else. So this is your alum. To find the formula weight of alum, you just use your periodic table and sum up the masses. I think it should end up to be 474 point what? Let me check. 0.39 or 36. Alum mass. What is the mass of alum? It's 474.39. If I Google it, probably you might find it as 36 from your periodic table summation, but it's close enough. So this will be the formula weight of alum. So we can now start doing the math to find the theoretical yield. And of course, to find the theoretical yield, you need the limiting reactant. The limiting reactant will be the one that will be completely used up after these 4 steps are done. That's going to give you the theoretical yield. So let's go to your report. Do you have a question, by the way, before I move from here? Do you have a question on the PowerPoint summarization of the summary of the synthesis of alum? Okay, so let's go to your report. Oh, before that, let me review. The limiting reactant must be found before you find the theoretical yield. The limiting reactant gives you the lowest amount of product possible if errors were not followed, if errors were not encountered, if you did everything perfect. Okay, and then to find the percentage yield, you'll have to use the actual mass obtained from your experiment and then divide by what you expected to get if there were no errors times 100. This would have been the setup for your filtration. You just pour your liquid in there after step 1 and use suction from your tap. This tubing is usually connected to the tap. As the water runs down the tap, you get negative pressure, which sucks the air out of the system. And that helps to filter your crude product. So alum will be trapped here on the 4th step. Potassium hydroxide aluminum reaction mixture will be filtered through here. The filtrate would have been used for step 2. Okay, so let's go to your report and do the math. So in your report 9, I've already given you the numbers that you need. I've given you the mass of aluminum for trial 1, trial 2. This is an actual result from last semester. So the volume of potassium hydroxide that was used is given. The molar of potassium hydroxide is given 1.4 molar for trial 1. Volume of sulfuric acid is given. Molar concentration of sulfuric acid is given as 4 molar. Actual yield after weighing the alum was 3.172 trial 1 and 5.200 for trial 2. So it's the same number posted down here, the actual yield of alum. So you will need to populate the numbers for trial 2. I'm going to walk you through trial 1 as an example. So let's find the limiting reactant, which will help us to find the theoretical yield and in turn find the percentage yield of the alum's product. So now you are given the reactants, which is aluminum, potassium hydroxide, and sulfuric acid. Those are the 3 reactants. Which of these 3 is limiting? We don't know yet until we do the math. We want the one that will give us the least amount of the alum. So let's test that by multiplying. So question number 1, and again, this will be for you to do for trial 2. I'm only gonna explain trial 1s. So number 1, it says show all the work calculations for trial 1 to find the moles of aluminum and the theoretical yield of alum if aluminum was limiting. So to do that, we have to follow a map. So the strategy map process will be, you want to convert, in this case, we are given aluminum is as mass. You want to convert the mass in grams of the reactant, which is aluminum, convert that to moles of aluminum, which is our reactant, and then using reacting ratios from the overall equation of reaction, we'll find the moles of product, which is the alum, and then you convert that to grams of product, which is the alum. That will be the process for this one. But what is the overall equation of reaction? So we have it right here. I'm gonna rewrite it, or instead of rewriting it, let me see if I can just copy it. So our interest right now is aluminum. For every 2 moles of aluminum, you're making 2 moles of alum. This is important because once we find the moles of alum, we can predict the moles of aluminum in our strategy and find the grams of aluminum, of the grams of alum. So let's go through the process. We were told in your table that trial 1 used 1 gram of aluminum. So moles of aluminum will be found by dividing the grams of aluminum by its atomic weight, which is 27 grams of aluminum. So 1 mole of aluminum is equivalent to 27 grams of itself. I'm putting the grams as denominator because I want my units to cancel. So now we are here. So we are left with moles of aluminum. We want to convert moles of aluminum to moles of alum. We have to use the reacting ratios. So for every 2 moles of alum, you need 2 moles of aluminum according to a balanced equation of reaction. And you have to show all these steps. So in that case, let's see. So now we have these moles of aluminum canceling. So the answer now is in moles of alum. So now we need to convert the moles of alum to grams of alum. We use this conversion factor at that point. We use the formula weight of alum. Remember, the formula weight of alum was 474.39. Just sum up the masses of the elements. 0.39 grams gives you 1 mole of alum. We're trying to test and see if aluminum is limiting. So we started by converting the mass of aluminum to moles of aluminum by dividing by its atomic number, which is atomic mass, which is 27. And then following our map, we have to convert the moles of aluminum from this step to moles of alum. So we use our reacting ratios. 2 moles of aluminum always gives you 2 moles of alum. We put 2 moles of aluminum down because we want it to cancel out. We want the units to cancel out. So use the reacting ratio 2 to 2 to convert the moles of aluminum to moles of alum. Next, we need the grams of alum. So we have to multiply the moles of alum by its formula weight, which is 474. Obviously, 474.39 grams of alum is equivalent to 1 mole of alum. These units are going away. Now we are left with grams of alum, and that's what we want. Punch the numbers on your calculator. I'm getting 2 times 474.39 equals 2. So we divide that by 54. I'm getting 17.57 grams of alum. Possible if aluminum was limiting. Next question, show all work calculations for trial 2 for you, for trial 1 for me, most of KOH, and the theoretical yield, assuming that KOH was limiting. So at this step, we have to find, we have the molarity and we have the volume of KOH. So the strategy will be to convert that to moles of KOH. Okay, we convert this to moles of KOH. And then from moles of KOH, we'll convert that to moles of alum. And then from moles of alum, we'll convert it to grams of alum. By the way, the answer we are getting here, we are looking at theoretical yields. All these grams are theoretical yields. So whichever starting material reactant that will give us the least theoretical yield will be the limiting, and in fact, the same process will in turn give us the theoretical yield. So we are killing two birds with one stone. So looking at the chart, we are given the volume of KOH to be 50 ml. The molar concentration is 1.4. Just like we did in the last lab, you do not want to use the volume in mLs. You want to use it in liters. And again, you need also the formula moles equals to concentration molarity times volume. That's why I'm saying the volume must be in liters. So we know that the molarity is 1.4 of KOH moles per liter. We know that the volume was 50 ml, so divided by 1,000 is 0.05 liters. Most of you had a problem with that whenever you are doing your experiment 7 reports. You don't know how to divide it. So this will in turn give you moles of KOH, which will be 1.4 times 0.05. The answer is 0.07 moles of KOH. So now that we have the moles of KOH, we'll need to convert it to moles of alum. Again, we go back to a reacting ratio. So if you're looking at KOH, the 2 moles of KOH are giving you 2 moles of alum. That's going to be our conversion factor. So we'll say these moles, 0.07 moles of KOH, will be multiplied by the conversion factor, which is a ratio of 2 moles to 2 moles of alum divided by 2 moles of KOH. Where am I getting these 2 moles again? I'm getting these numbers from the equation, balanced equation of reaction. The ratio is 2 to 2. For every 2 moles of KOH, you get 2 moles of alum. So we need to convert the moles of KOH to moles of alum. That's why my moles of KOH are the denominator. Moles of alum are on top. So now at that point, we have moles of alum. If you have a question, just unmute your mic and ask. Others, I'll keep flowing. So we have moles of alum. We need grams of alum. So we do the same thing. We multiply by the formula weight of alum. For 1 mole of alum, you get 474.39 grams of alum. Okay, so I'll put the mass on top, numerator, and then I put the mole value as the denominator. Okay, so we cross out the SI units. Do the math on your calculator. Let's see. Did I do something wrong? 0.07, 474.39. So I'm getting the answer to be 33.2. Significant fingers, how many? I think it should have been 2 significant figures. So let me say, I'm getting the answer to be 33 grams of alum. Okay, so far, potassium so far aluminum is the limiting reagent, because when we tested for 1 gram of aluminum to see how much possible mass, how much maximum mass possible for alum obtainable, we found 17.57 grams. But if you assume KOH is the limiting, the theoretical yield is 33. Obviously, the aluminum is the limiting. Give me a minute. Okay, so next we are doing the testing of sulfuric acid to see if it's limiting. Going back to the table, we see we are given the volume and we are given the concentration. So we do the similar step, a similar strategy. We have to convert the molarity and the volume to moles. Okay, and then we use our reacting ratios to find the moles of alum and then convert that to grams. So we are given the molarity, we are given the volume of the acid, and let me see. So the volume of the acid is 20 ml, concentration of the acid is 4 molar. So again, I don't want to use the volume in mLs, I need it in liters. So I have 4 moles per liter. We are multiplying that by the volume, which is 0.02. Okay, liters, L and L will go. So the moles of sulfuric acid used in this case will be, I think it's 0. This is liters, it's not 4, I'm just canceling it. 0.08 moles of sulfuric acid. Okay, now to find the moles of alum, we'll have to use the reacting ratios and just convert it to moles of alum. We'll look at the balanced equation and see what is the reacting ratio. So in fact, looking at the balanced equation, I see for every 4 moles of sulfuric acid, I'm getting 2 moles of alum. That will give us the conversion factor. So I'll come down here and say, okay, I need the moles of the alum. I know the reacting ratios. For every 4 moles of alum, which is the product, oops, my pen is not writing. For every 4 moles of alum, I need, let's see, it's the other way around. For every 2 moles of alum, sorry. Okay, the document is misbehaving. For every 2 moles of alum, I need 4 moles of sulfuric acid. Okay. So this helps me to cancel the units. That's how I know who needs to go down. And then at that point, I have the answer as moles of alum, but I need the mass of alum. So I'll do 474.39 grams of alum, 1 mole. 1 mole of alum is equivalent to 474.39 grams of alum. So now I can cancel out the units. I can cancel out the units, and the answer will be in grams of alum. Let's do the math and see the theoretical yield if sulfuric acid was limiting. So times 2 times 474.39. Okay, I'm dividing that by 4. So I'm getting the theoretical yield of alum to be 18.97. Let me say 8.98 grams. That would be the theoretical yield of alum if sulfuric was limiting. Now let's compare the 3 guys. I have 18.98, 33 grams, and 17. So 17 is the least, which means that aluminum will be the limiting reactant because it gives you the least amount of product as per the definition of limiting reactant. So aluminum is limiting you. It's limiting you in terms of how much you can get from the product, from the reaction. So it's the limiting reactant. So now that we know that, can we find the percentage yield for trial 1? Yes. Percentage yield is given by dividing your actual over theoretical yield, and then we're multiplying by 100. So what was our actual yield on trial 1? My actual yield is 3.174. So I'll say 3.172 grams. I'm dividing that by the theoretical yield. Remember, we determined aluminum is limiting. The theoretical yield for aluminum turned out to be 17.57 grams. So we come here and say 17.57 grams, and then multiply everything by 100. So we are canceling that and dividing. So 3.172 divided by 17.57. Remember to multiply by 100. The percentage yield I'm getting here is 18.05%. Now, how do I determine the significant figures? So I'll go back to my theoretical yield calculations and see what the significant figures were provided. Obviously, I need to go to the table. So it's 4 significant figures that I'm given in the table. This one was 4 significant figures. So that's why I reported this in 4 significant figures, and that's how I report this in 4 significant figures. So it depends on the numbers you're given in the question. So that will be the process that you'll do to do the math for trial 2. You're given the numbers, fill up this chart. I've done all this. You can find your moles going down the table. Remember, to find the moles of aluminum, it's just simply this part right here. That will give you the moles of aluminum. Okay? Mass divided by the atomic mass. Given mass divided by atomic mass. And then to find the moles of sulfuric acid, I showed you how to find the moles of sulfuric acid. Where is it? It's right here. Remember, moles equals to molarity times volume. Volume must be in liters. So that's how I found it. Next, theoretical yield of alum formed from aluminum. Of course, that tended to be a limiting reactant. We did that math on this part right here and found the theoretical yield to be 17.57. Al is limiting. That goes onto your table right there. Theoretical yield of alum formed from sulfuric acid. I've shown you the process right here. Theoretical yield turned out to be 18.98. For trial 1, you do the same thing for trial 2 and see if you find the same answers. And then theoretical yield of alum is what you got from the limiting reactant, and then actual yield is given, percentage yield is just what we just did. Do you have a question on the explanations or no? Question? No question. Okay. All right. Again, last reminder, this report is short-lived. You have to do it as soon as you can and send your report in. It's very simple to do. I've walked you through all processes. I don't see any difficulty there whenever it's time for you to do it. So see you next time.